I'd like you all to think back to a one-star review that you read on the App Store. Probably the word crash was in there. And we know by now as app developers that using a crash reporting system is a pretty effective way to limit the number of bad reviews you see. What you might not know is how those reports are actually generated. My name is Massicotte. I've been working on iOS crash reporting for about 4 years now. I'm going to give you some insight into what goes into our SDK, talk about some of the challenges that we've faced, and some of the ways that we've overcome them. I'm going to get started with what might look like a funny question. But after all, this is exactly what we're talking about. Now, when your app is running on a phone, it looks like it's got the whole thing to itself. CPU, RAM, all the hardware, it looks like it's not sharing it with anything. But in reality, you know that there's lots of other processes running on that device. The way that this is done safely is that the operating system collaborates with the hardware to impose some rules about what your process can and cannot do. And breaking one of those rules is one way that your process can crash. Let's take a look. The first one I'm going to show you is one of my personal favorites, the null dereference. So on that first line, we're setting a pointer to be null, which is just another word for address 0. On that second line, we're going to try to write to that address. The reason this crashes is that when your process has been started up, the virtual memory system has been configured in hardware to disallow reads or writes to this address. So when that second line gets executed, what will happen is the hardware is going to actually trap into the kernel. The kernel is going to realize it was your process that was running and broke this rule, and that's when the crash is going to happen. Now, there are other ways to bring a process down besides just breaking one of these rules. In fact, it's very common for processes to terminate themselves. This might sound weird. I'll give you an example. So suppose your app communicates with some server somewhere, and it might need an address. And you might have some sort of assertion somewhere that says, this address can never be null. Perfectly reasonable, and if it is null, you can't really make reasonable forward progress. This kind of situation is so common that Swift actually has a built-in function to describe exactly that. It's called fatal error. How it works is you can provide a string that gives a little bit of context, and then what fatal error is going to do, it's going to execute an undefined instruction. And what happens is the CPU is going to object to that instruction. It's going to trap into the kernel. The kernel is going to realize it was your process and crash, similar to the null dereference. Another one that I'm going to talk about is going to look real familiar to Objective-C developers. This is an exception. In this case, it's an array out of bounds. The reason why I bring this up is that technically speaking, this is not a crash. What's going to happen on that second line is the runtime is first going to search for an appropriate catch statement, and only if it cannot find one is it then going to execute abort, which undefined instruction, CPU, kernel, crash. So these are some examples of fatal events, but how are we going to detect them in the same process that they occurred in? Well, there's actually a variety of APIs available on iOS and OS X that we can use. Let's take a look. The first one is defined in nsexception.h, and it's real simple. When that runtime is doing the search and it's decided there's no appropriate catch, before terminating the process, it will allow you to run a little bit of code, and you can do whatever you want there. This is useful because it's simple, it's really convenient, but unfortunately, there are lots of kind of crashes that are not related at all to exceptions. So if we want to catch those, we're going to have to use a different kind of API. The first one we're going to look at is POSIX signals. Now, signals are kind of similar, but they work in a funny way. So here's what happens. Suppose that null dereference is happening again. And what's going to go on is you hit that second line, and then control is going to be immediately transferred to your signal handler. It's kind of like a magical goto. And kind of like goto, it can be problematic. In fact, if you read the man page for SIG-action, what you'll find is that it lists a very small set of APIs that are actually safe to call from a signal handler. The reason for this is that the vast majority of functions are not set up to be interrupted in this asynchronous way. So this does sound maybe tricky but useful, but in fact there are a bunch of fatal events that can occur on iOS and OS X that are not mapped directly to POSIX signals. To catch those, we're going to have to use another API called mock exceptions. These are not to be confused with runtime exceptions. Similar name, totally different thing. They actually work pretty similar to POSIX signals. So what happens is you start up a thread and you park it waiting for one of these mock exceptions to come in. And you got another one going. Let's say it does that null dereference. Well, when that happens, that thread gets stopped, and the kernel wakes up your parked thread, and it gives it information about what thread broke what rule. Once we have all this information here, what are we going to do? Well, this is kind of key. See, crash reports can tell you what happened, but they cannot tell you why. I like to think of crash reporters as like an investigator at a crime scene. They're gathering up a bunch of evidence, but it requires a human to do some kind of interpretation. And that could be you looking at a text-based crash report, or it could be someone looking at an aggregated group of crash reports on the Crashlytics dashboard. The point is, it requires a person to do some kind of interpretation. And most likely, the thing that person is going to turn to first is something called a stack trace. Let's take a look at one. So this is an example of a crash that I caused in a little test application. And you can see there at the top, crashed in Objc message send. The reason that that happened, you can kind of guess by the name of the next function. Crash messaging bad address. So what I did was I called an Objective-C method on a pointer that was not really pointing to a real Objective-C object. Now down below that, you can see some table view stuff. So you might imagine maybe I have some sort of table of crashes that I can cause. Below that, you see some run loop machinery, not very relevant here. And then below, you can see that this thread, it was a main thread, and you can see where it started. Now this is great, because if you start at the bottom and you look all the way at the top, you can get an idea of all the functions that were called to get this thread into its current state. But here's the problem. At the time of crash, we don't have any of this. So how do we proceed? Well, the first thing that we do is we ask the operating system for the current state of machine registers at the time that thread crashed. There's a whole bunch of them. We're going to talk about two in particular, the PC and the SP. Now, inside of the PC, stands for program counter, is the address of the currently executing instruction. And that instruction is inside of the Objc message send function. Using a process called symbolication, we can take that address and we can turn it into the Objc message send string. And already, this is kind of useful on its own. It gives you some idea of what this thread was doing. But it's not enough context here. What we really want is that next function down. To get that, we're going to have to make use of the stack pointer, SP. And that's just an address that points to the bottom of the stack. Now, the thing to keep in mind is that every time a function is called, some information about its identity is pushed onto the stack. The thing is that lots of other things are pushed onto the stack too. You got local variables, function parameters, and the thing that makes this hard is that there's no way to distinguish some data from the other. The stack is a completely opaque data structure. But if we could somehow find that address on the stack, then we could use the same process of symbolication to fill in that next frame. And if we could get all the addresses off the stack, then we could fill in our whole stack trace. This process is called stack unwinding. And the thing I'm trying to impress on you here is that when it comes to stack unwinding, the details of the underlying machine really matter. You have to understand the CPUs, the registers that are involved in function calls. You have to understand how the compiler generates the code for functions. And you have to understand how the stack is involved as well. All of these things make up something called an ABI, Application Binary Interface. When it comes to stack unwinding, the ABI really matters. Now, luckily for us, crash reporting is not the only system that needs to do stack unwinding. Your debugger, for example. When you stop in a breakpoint, your debugger is going to show you a backtrace. Another interesting thing that uses stack unwinding is the exception propagation mechanism. That's kind of weird, but when you go from a throw to some catch somewhere else, you need to do stack unwinding. So we do have some options here. Let's take a look at what they are. The first, something called frame pointers. Frame pointers are great because they're really simple. The way they work is that when the compiler generates the code for a function, it inserts a little extra bit of information onto the stack. That transforms the stack from an opaque structure into a simple linked list. You can go from your current function, follow this pointer to the next, and all the way up to the top. Another great thing about frame pointers is that they're really common on all the architectures that Apple uses. So almost all functions that you'll encounter will have saved a frame pointer. But that's a key word, almost. Not all functions are going to save them. And in fact, that crash we just saw, Objc message send, it does not save a frame pointer. So what are we going to do? Well, those debugger engineers, they all got together, and they built a standard called Dwarf. And there's a section in that standard called dwarf CFI. It stands for Call Frame Information. Now, I guess because this was a standard and it was designed by committee, maybe, this standard is highly, highly complex. The reason why is it needs to be able to describe stack unwinding for an arbitrary machine and of arbitrary complexity. To do that, it needs to be able to describe all possible register state mutations. What that means is, if you find yourself halfway down a function and you know the current set of machine registers, it can tell you what those machine registers were at the time that that function was called. To do this in a space-efficient way, dwarf CFI makes extensive use of compression and a stack-based virtual machine. What this means, at the time of crash, when we're doing stack unwinding, sometimes we need to read this dwarf information, parse it, initialize a little virtual machine, run some instructions, in order to be able to reproduce the register information that we need. This may sound kind of crazy to you, and it sounded crazy to Apple as well. So they invented another format called compact unwind. Compact unwind is really neat. So it's not quite as simple as frame pointers, but it is significantly simpler than dwarf CFI. Because of that simplicity, though, compact unwind cannot describe all possible register mutations, but it can describe many. And here's how it works. It's interesting. So when you query the compact unwind information, you're going to get back one of three possible results. It may tell you, yes, this function did in fact save a frame pointer, and it's safe to go ahead and use it. But it may tell you, no, there's no frame pointer, but here's a small set of operations that you can use to reconstruct the registers you're after. Now, a third possibility is it just can't describe this function at all. And in that case, it will give you a pointer into the dwarf information, so at least you can save some time while you're parsing. Compact unwind is pretty cool. Another interesting thing about it is that even though technically speaking, dwarf CFI is supported on ARM64, practically speaking, you'll never run into a function that actually requires it. Basically, all functions on ARM64 are describable using compact unwind. Now, I've been talking about these custom binary formats and a virtual machine. And remember, we're running all this stuff after your process has already crashed. So you've got to be wondering to yourself, is this even a safe thing to do? And the answer to this question is no. Sure, we try to be as safe as possible, but the reality is sometimes failures are going to happen. And so we've built that into the philosophy behind our iOS SDK. We assume there will be deadlocks, or there will be corruption. And we've designed in such a way to try to still deliver useful reports even if those things happen. I'm going to talk a little bit about how we did that. But first, I want you to remember, when I was talking about those signals and mock exceptions, is that at the time a crash occurs, you have to know that your threads are all in arbitrary states. What that means is you might have one thread over here that's allocating an object. That means it's in malloc, and malloc takes locks. So our SDK cannot allocate memory. Then you might have another thread over here that's calling an Objective-C method, and you probably do. Right? Well, it turns out that the Objective-C runtime itself also takes locks, so we can't use that language. This might sound pretty restrictive, but actually, it gets far, far worse. Take a look at this statistic. See, we instrumented the crashes coming into our system, and we found that 45% of them are somehow involved in invalid memory accesses. Some of those are real simple, like that nullity reference I showed you earlier. But some of them are going to be use after freeze, or over releases, or buffer overflows. These are the kinds of events that can cause your process to sustain significant damage before it ends up crashing. Now, you know what the second most common cause of crashes is? It's uncaught exceptions. That probably doesn't sound too surprising, but if you look more closely at what is actually happening with those exceptions, well, in many cases, they're the result of something called heap corruption. I'll give you an example. So this is something that a lot of Objective-C developers have seen before. It's the unrecognized selector exception. So you're looking at the crash, and the stack trace makes perfect sense. You know that your application does take this call path. And you're looking at the method, and that makes sense too, given the context. But it's the object that's weird. You're calling it on some sort of underscore underscore NS concrete mutable string. Like, what is even going on there? Well, it's heap corruption. You got a perfectly reasonable pointer that is no longer pointing to the object that you expected. And who knows when your object graph went wrong. So if you just take those exceptions and you attribute them as well, It could be as many as 70% of all crashes are the result of some kind of memory corruption. Now, I know that there are some Swift developers in the audience who are thinking, but this is like a C, an Objective-C thing, I don't have to worry about this. And it is true that Swift is significantly safer in some cases. But I don't want you to forget that your app is making use of literally hundreds of libraries that are made up of millions of lines of non-Swift code. And all it takes is one bug in one library to cause significant damage to your process. This is the real challenge that our SDK faces. We need to be able to withstand this kind of damage and still produce a useful report. I'm going to show you some of the strategies that we use to do just that. So here is this is a diagram of your app's memory. You can see there at the bottom, you have the Crashlytics data structures, and there's a pointer to some app metadata somewhere else in memory. Don't worry, this diagram is not to scale. I just need a little space to illustrate my points. So suppose that some bad write comes in. It overwrites that metadata. Say that this was your app's bundle ID. You probably have no reason to even read this memory. So even though that bad write happened, you probably didn't crash. In fact, you're running along perfectly happy when all of a sudden, for some other reason, you do crash. Well, that's when the Crashlytics SDK springs to life, right? It starts collecting information, it's unwinding these stacks. And what do you think is going to happen when it dereferences that pointer? Well, the best case scenario is we're going to write out some corrupt information. But worst case is that we ourselves are going to crash. So we combat this using 3 techniques. The first is real naive. We do more sophisticated checking on pointers than just checking for null. It sounds silly, but there's actually a whole bunch of heuristics that you can use to verify whether a pointer even could be correct, and it catches a surprising number of failures. Another trick that we use is, instead of reading that memory directly and possibly risking a crash, we do it indirectly via an OS function. So instead of crashing, the OS will just tell us, I'm sorry, I couldn't read that. The last thing that we do is really interesting. We make use of a corruption-resistant data format on disk. What that means is that even if we do write out corrupt information, it is highly likely the report is still machine-readable. In fact, this is happening every day, and our customers aren't even noticing it. Now take a look at this next situation. Suppose this happens. The Crashlytics data structures themselves have been overwritten. This happened to a real customer of ours. And I'm not going to lie, this was a tricky one to debug. But when we found out what was going wrong, what we really realized is that having anything in RAM, the more code we run, these are all examples of liabilities. We need to minimize what's in memory as much as possible. But we can't get it to 0. So we split up our memory into 2 regions. You've got a very small readable and writable section, and another section that we found we never wrote to, we just read. So we actually mark that section read-only using the virtual memory system. It cannot be overwritten. But we didn't stop there. We also inserted these 3 sections called guard pages. And what they are is minimally sized regions of memory that are neither readable nor writable. So imagine now that that bad write were to come in again. Well, the first thing is our data structures would be safe. But another great benefit is you'll crash as soon as you hit that guard page. And this is wonderful, because it means that the crash is more close in time to when the report gets written out. So you have a much higher likelihood of being able to identify the issue and solve it. Now, so far what I've been talking about is all related to reliability of writing out the data. But that's really the first step. Because even the most perfect crash report that's on some user's device, if you don't see it, it's totally useless. We need to be able to transfer these reports as reliably as possible. To show you how we do that, I'm going to go through a crash that I'm sure every app developer in this room has seen before. It's the crash on launch. This one is a bad one. And this particular scenario, what I'm going to be showing you is a timeline of the subsequent launch. So the app has crashed, we've saved out the data, and it started up again. So the app starts up for the second time, and there's Crashlytics getting started. So it notices the report's been saved, packages it up, and it queues it up for an upload to our system. But suppose that crash was caused by some kind of messed up on-disk cache. That cache is still there, and that means the crash is going to happen again. Well, if that happens, the process is going to come down, but our SDK is running inside of the same process. So this upload is never going to finish. Well, one way to deal with this problem would be to just do that upload synchronously. And that can work. It's not the best, because our server may not be accessible at that moment. The user might just not have internet access. And also, we only have so long to let your app start up. Plus, it's really annoying to delay start. So what we do instead is we queue up a background NSURL session upload. This is a really amazing thing, because it allows that report to be uploaded reliably, even if your app never starts up successfully again. And this is exactly the kind of time when you need that report. Now, the reason why we spend so much effort in reliability of transmission and in reliability of reporting is because that we believe running in your process is a really big responsibility. We want to make sure that you get the stability information that you need to build the best applications. My name is Matt, and I'd love to talk to you and hear any questions you have. I'm going to be at the happy hour later. Thank you very much.